Hey guys, welcome back for another, not a long lesson. We're going to get into chapter 9 today, just drive into that. And to me, you'll see this thing called hybridization. To me, it really explains how dots works, and it goes right along with shapes and bond angles. And I don't know how far we're going to get into it, but that's what we're going to be doing in chapter 9. Hoping we're going to get done through. Again, we're only going to cover half of chapter 9, so because I just really know we got to just move as fast as we can to be getting through just as much as we can, getting ready for the AP test. Okay, jokes though. What has two hands? This is a riddle. Two hands, a big round face. Two hands, a big round face, always runs but stays in place. I'll say it again. What has two hands, a big round face, always runs but stays in place? A clock. And what did one knife say to the other knife? You're looking pretty sharp today. I like that one. I thought that was pretty good. Okay, so where we were, so we finished chapter 8. We talked about all the dots and shapes and bond angles and polarity. Okay, so now into chapter 9. Okay, and just, again, not a super long lesson today, but getting into it a little bit here. Okay, and to me, chapter 9 and this whole idea of hybridization, and again, there's more than one model. I'm going to talk about that today, but there are two theories on how atoms bond in molecules. Okay, so again, for those that are taking notes, I'll give you guys a minute to write this down. One of them, the one we're going to learn about, is called the valence bond theory. And it's called localized electron model, and I'll explain what I mean by localized electron. But atomic orbitals of atoms overlap to form bonding orbitals. Electron pairs spend most of their time in between the two atoms. And that's what the localized means. And then here is H2. Okay, so let me kind of just analyze these two theories. I'm going to write on the board. And we're not going to cover theory 2. And it's in the second half of our book. And if you guys, again, took chemistry past our class, you would do that. But here's what we're going to learn about. This is this valence bond theory. It's theory 1. What it says is this, is that if we've got a nucleus and we got electrons here and we got another nucleus and we got electrons here, the electrons here are said to be localized. And that means they're right here, localized. We can identify where they are at. This is what's called, again, it's called the localized electron model, and some people call it the valence bond theory, and I'm going to talk, that's what we're going to be spending our time about. And this is where I just define this, the atomic orbitals of atoms overlap to find bonding orbitals. Now the other theory, which is called the molecular orbital theory, which we are not going to get into. It's not going to be on the AP test. It's not going to be on our test. And I think my understanding is, and this is if you took chemistry in our college or in college beyond our class, you would get into this. But in this model, there actually is, I guess, on some of the bonding, it explains some of the things maybe a little bit better. What we're going to learn about, to me, makes sense. But in this model, if I've got the nucleus and the electrons and the nucleus and the electrons, well, what this says is the electrons are out here. They are the electrons, E negative, the electrons are delocalized. Okay, so they're out here. And what that means is the electrons you can't, like here in the model we're saying, is that the model that we're going to be using and talking about says that the electrons are located right here. This model, the molecular orbital model, says you can't, the electrons are not in a specific location. And again, this model, I guess in some forms of bonding actually does a little bit of explanation better. I think this model is kind of makes sense. And then I had in the notes H2. So if we go back, and again, to me, what this is saying, what this is explaining, is this is explaining how dots work. So if I have H2, so what this is saying is that if I go back to the electron configuration, so I have H and H. So I go back to the electron configuration, so I have 1s1, 1s1. So what I have here is I have this 1s orbital with a single electron. I have two of them, and they bond. And that's what happens here. And that's why in that illustration, I'll go back to it that I had in the notes. So what we really have then is we have H connected to H, and that is these electrons right here that, again, are localized. They are between the two nuclei, and these two electrons are involved in the bonding. And that's why when we did the dots, we looked for the single dots, and we paired them up is what we did. Okay, so then if I go back, do a couple more examples here. Okay, so, and if you look on the bottom, this is what I was trying to talk about. So H2, so you have an H and an H, and then when the two bond together, those two electrons are localized. They are found in the middle between the two nuclei. Okay, so here's the next one. So same thing. So I'm going to come back and do this on the board. I'll do this F2 with the valence bond theory or the localized electron theory. And so you can see that if you have F2, and I've written in the electron configuration of one of the Fs. So you've got, again, that what you're looking for, what this model is saying when you have that half-filled orbital. So an orbital with a single electron, it is looking to pair up with another orbital with a half-filled orbital with one electron in it. And then you can see there with those little green balloons, so those half-filled orbitals pair up, and that's what this model is saying. So if so again, if I go back, if I go to the board, so if I had F2, so again, simply put, what this model, what this is doing in chapter 9 is we're explaining the dots. We're explaining how does the bonding work in the dots. So for F2, so I've got two Fs. So the electron configuration is 1s2, 2s2, and then it's 2p5. And the reason I'm writing out two Fs is because it's F2. So if I did the orbital diagram, I have the 1s2, there's the 1s, then I have the 2s, and then I have the three 2p's. So here we go back to stuff that we were doing before, back before Christmas vacation, back in December. So what we have again is this, just exactly what I was showing. I showed there on the overhead page. Well, this fluorine is the same way. So we've got 1s, we have 2s, and we have the 2p's. This. And then the bond is, it's this right here. And this aligns with the dot structure. So here was fluorine, here was another fluorine, and we just paired up the single dots. Here's we're pairing up the single dots. And these are really like, if you look at it, like here's the 2s, and here's the 2p's. So again, here's the 2s, or however you want to call them, and there's the 2p's. And there's the bonding electrons, and the 1s is indicated in the structures. So that is how chemists are explaining what is going on in bonding. Okay, so here's another example. So here's HCl. So the H is over there on the left with the 1s1. And then there's the chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. But again, orbitals that have half of an electron or have one electron, they're half filled, those are the ones that are going to bond. And again, the electrons are said to be localized because they fall between the two nuclei. So you can see the diagram there on the bottom. Okay, so if I diagram this, so HCl, so if I've got HCl, so the H is 1s1, so there's again a half-filled orbital. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. And really, we just need to look at the last entry. All the others are going to be filled, but I would have, so here's my 3p's. So here's 3p5, so here's the 3p's. So look like that. So again, here's a half-filled orbital, so these are going to be the bonding orbitals. So when we do the dot structure for H and Cl, so here's H and then Cl, and again, you can imagine this is 3s2, and then here are the half-filled 3p's. So explaining again how bonding works. And then, so then what comes along is this. Okay, so then what comes along is this. So CH4. So there's a whole bunch written down here. So I'll just give a minute for you to look at this, and I'll talk about this, and then this is probably where I'll stop, because carbon kind of gets into this idea of hybridization. Okay, so I'm just going to write on the board here. And again, what we're doing here is we're really just explaining the dots is what we're doing. Okay, so if I'm doing CH3, so again, let me go back to what I've been doing, or CH4, so methane, CH4. So if I've got a carbon, which is 1s2, 2s2, 2p2, and hydrogen, which is 1s1, and there's 4 of them. So 4. Okay, so if we go back again, we're looking to pair up the orbitals that have a 1 electron in them. They're half filled. So here, if I did so here's 1s. I'll just do the whole thing. So here's 1s. Here's 2s. Here's the 2p's. Hey. Hi, Bonnie. So here's the 2p's, 2p2. So we have here and here. So what we have is we have 2 half-filled orbitals. Okay, and here 1s1. So each one of these hydrogens is like this. So you look at this and you go, wait, this doesn't work. This doesn't work. There's only 2 available spots here where I need 4. And when we've done the dot structure for this, we have carbon. And notice how we write carbon. We write carbon with 4 single dots. Well, that doesn't seem to align by this. And so this is how chemists explain this. This is the idea of hybridization, which is on the board, and we're going to come back to on Thursday and Friday. But one of the 2s electrons, this is the theory, this is the idea, is promoted up here. And so what I have now are I have 4 equivalent orbitals. So if I write this down, so I'm going to just change this. So I still have the 1s, but what happens now is these orbitals all hybridize. And I play golf. I don't play very well, but I play golf. And in golf, they have clubs that are called hybrids. And a hybrid is kind of like an iron, and it's kind of like a wood. It's kind of a cross between an iron and a wood. Well, that's what happens here. This is what this model says. And these orbitals, which now were distinguished, the S and the P, they hybridize. And what we have then is this. Is we have 4 equivalent orbitals, and they're called sp3, and they are hybrid. They're hybridized. So again, like in my analogy of a golf club, they're hybrids, so they're kind of like woods and they're kind of like irons. Well, these sp3 hybridized orbitals are kind of like an S and kind of like a P. So what we've got then is we have 4 single orbitals, and they can bond just like this. And that's where we get the dot structure here. And then what also happens here is their shape changes. Remember, s orbitals are spherical, their shape, and p's are like hourglass or dumbbell. Well, when they hybridize, what they do is they have this little node kind of from the S and then like this. And this is what the sp3 hybridized orbitals look like. So definitely something new and definitely something to look into. So hopefully you guys watch this. I'm going to kind of re-explain this a little bit on Thursday, just exactly how this hybridized orbital works. So hopefully that makes a little bit of sense, definitely a little bit confusing, and we will revisit that. So guys, have a good day, and on Wednesday or Thursday we will Google Meet again. We'll get into more of this hybridized stuff. Have a good day.